Shrikant, so we begin now. Okay, so we begin the lecture now. First part of the discussion would be about Krylov-Safonov theory. Now, why do you require that? Okay, so as I said, for the Banerjee-Nashmoser theorem, the context is that you look at a function. Okay, you look at minimizers of this. So this is the divergence form theory, is that you want to look at the minimizers of these variational integrals, and then the u is minimum if and only if it is a weak solution. Right? Now what you do is that you put one derivative inside, okay? You differentiate this Euler-Lagrange condition, okay, in some direction ek, then what you get is dij. So fi I should not write. So what I do is that so this is fine. So fi I have to say fi is f in the direction here. So p, so f is a function of p, and p equals to p1 all the way up to p. So in one of the okay, so this is the Euler-Lagrange condition. Now what I do is that I differentiate it with respect in one unit direction ek. Okay, so then what you do is that because of the translation invariance of this, you put this derivative inside. So this becomes di of fij value, and then inside at the jth place you differentiate by k. So that becomes u jk equals to 0. Right? So now I can switch the order of the derivative, at least formally, which get uk j equals to 0. And now, mostly for many of these theories to work, what you require is the convexity of these functionals, right? Convexity of these functionals translates into ellipticity of this coefficient matrix. So this is your Aij. So the Hilbert's 19th problem was whether the minimizers are smooth of these, if the functional is smooth. Okay. So in the end, what you see is that the directional derivatives are solutions to. So if I call uk as my v, then I have that v solves divergence of a grad v equals to 0, v equals to uk, and this happens for every case, right? What is this a? A is this matrix. So even if I know that f is smooth, but then from the general theory, I only get that u is in W22. So that doesn't say, even if f is smooth, but because the dependence is on u, so you cannot say anything about certain regularity, right, of these coefficients. So what breakthrough Banerjee-Nashmoser made was that, or Banerjee and independently Nash made was that, they showed that if you give me any uniformly elliptic structure, then this v is C alpha. So C and M implies that v is C alpha. What is v? V is uk, the derivative of u. But then you can do it for all case, and that tells you that this coefficient matrix is C alpha because f is smooth. So then you start. So once you cross this barrier, you get that A is in C alpha. But then you can apply the small perturbation theory. The shorter theory will tell you that this V will then be C1 alpha. If V is C1 alpha, it means that the derivatives of U are C1 alpha. That means that this coefficient matrix is C1 alpha. And then this V becomes C2 alpha. So once you cross this barrier, which is facilitated by the Banerjee-Nashmoser theorem, you can bootstrap it and get all the way up to C infinity. So the bottleneck to the solution of the Hilbert's 19th problem lied in crossing this threshold. And that just tells you that minimal surfaces, graph minimizers cannot have contours. Okay? Now, even only because of convexity. Okay, so you can go from the extrema condition to that. So, of course, I mean, if it is not convex, then you can have some part of the theory. But what convexity tells you is that planes have to be minimized. Okay, roughly. So now the thing is that now we go to the non-variational theory. So the non-variational theory is about, it is the non-divergence counterpart of the de Giorgi-Nash-Moser theory, non-variational theory. So I start with F, an operator on matrices, okay, such that it is strictly positive on the in the cone of positive definite matrices with some quantitative parameter. That is, this is less than equal to f of m plus some big lambda, which are the ellipticity parameters. So you write it as n plus minus lambda n minus. So any n has a positive part and a negative part. And then you also assign a similar bound from below. This is bigger than equal to f of n plus little lambda n plus minus capital lambda n minus. So in the case when n is positive, you don't see n minus. So you see that there is a strict growth in the cone of positive definite matrices. This is what ellipticity is. Why? Because if I take n to be the following way, so for any direction u such as e equal to 1, okay, if I take n to be E transpose, and if I put this condition, okay, and then from here, by substituting this value of n, what you are getting is that del f, del ij of ei, ej should be equal to 0, which is the ellipticity condition. Okay? Clear? Because what you are doing is that this is a positive definite matrix, right? Is it positive semi-definite matrix? Why? Because if I take E transpose, okay, and then if I sort of want to do it on an E vector psi I get this is simply Ei, Ej, psi I, psi j, and this is equal to E inner product of psi whole square, which is bigger than equal to 0. So this is an admissible direction in the space of matrices when I can apply this, and I would be able to get this condition. So I mean it's very simple. So what you do is the following. So in fact what you get is that this is bigger than equal to little lambda of E square. That is what I want to achieve. Okay, bigger than equal to 0 is the form statement. So how do you do that? So what you have is that you apply the condition on any m, f of m, there's some t of ti, t tensor e. That is what this E transpose is. And then this you know is less than equal to f of m. Let me do one side. F of m plus little lambda times t times e cross e. Okay. So if you see what is the total norm of this, this is like morally lambda times c. So let me just write it e cross. Okay. So then I put it back. I get f of m plus t e cross e minus f of m by c. This is bigger than equal to lambda times e cross a, which is norm of e square. Okay. This is essentially the matrix norm, right? So now the thing is, what is this? If I derivate this, I have to apply chain rule. If I derivate this, this is simply telling you that f of e of m of ei ej if applied to e is bigger than equal to 0, right? Or t square, right? And if I expand it, this simply becomes del f del ij m square ei ej is bigger than equal to lambda x square. So norm of e is 1, okay? And then you can solve it. Is it clear? And likewise, you can get a bound of this side. Yeah, so it is kind of strictly positive in the cone of positive definite matrices, okay? In a quantitative way. Why do you care about this theory? Okay. Well, these kind of operators appear in a variety of situations. So, for instance, take R2, and if I look at this equation, I want to solve this PD with some boundary conditions. Now, from the general theory that I will develop, I can show that existence uniqueness, and I can get classical solutions, C2 alpha solutions. Okay, so that will be done towards my line. But this is a highly nonlinear operation. At every point, you are computing the Hessian, and then you are comparing which of this is larger, and then you are saying that the max of this is 0, equating that to 0. So point by point is a very nonlinear operation. And at least from my knowledge of the theory, it is almost impossible to say when you make a transition from one operator to the other. So the phase transition is a very complicated thing to study over here. Okay, but from the general theory, which will be it is the convexity in this case, will tell me, because it's a envelope of a family of linear operators. The max of this, you can eventually tell, which is the Evans-Krylov theory, that the solution is C12. That is later. Okay. And the other operator is the Monge-Ampere operator. It shows up in a variety of contexts, especially the prescribed Gaussian curvature problem, optimal transport, and so on. Okay, so let me skip any further motivation and let's get straight to the details. Okay, this is all motivation for now. Okay, so now let's understand this. So I'll just assume that f of 0 equals to 0, and if you solve f of b square u equals to 0, what is this telling you? What this is telling you is that if I sort of match this condition, that will tell me that f of b square u, which is equal to 0, is less than equal to capital lambda of b square u plus minus little lambda b square u minus, right? And on the other hand, this will be little lambda b square u plus minus capital lambda b square u minus. Okay. Now from each of the sides, from this side, this is the quantity which is 0. This is bigger than or equal to 0. So what you get is that capital lambda times b square of u plus dominates little lambda b square u minus, and also the other way. B square u minus is bigger than or equal to little lambda b square u plus, right? This is what you get from this ellipticity condition, right? So this is just telling you that point by point, b square u plus is comparable to b square u minus, right? Because the positive part and the negative part of the matrices are controlling one another in this quantitative way. And now, what is the thing that we want to do? We want to see how to sort of apply the same scheme that I described over there to this fully nonlinear structure. So what is the first thing that you would do? You would differentiate this structure, right? So if I have f of b square u equals to 0, I derivate it inside, okay, in some direction e. What do I get? I get del f by del ij of f of b square u, and when I do the ij direction, I get uj I of e equals to 0. So what I do is that I can put this in. If I put this in, this becomes ue of ij equals to 0. Now, again, because of uniform ellipticity, which is enforced by this, or where else it is? So lambda of e square. Okay, this is the ellipticity condition. So if I look at this matrix Aij, this is positive. This is what? This is positive definite, right? Positive, uniformly positive definite. So therefore, I have that ue equals to b solves Aij, Bij equals to 0. So the Krylov-Safonov theory is about showing that B is C alpha. Okay? And then if B is C alpha, then UE, this will imply that UE is C alpha, and therefore U is C1 alpha, right? Formally. And all these things are justified by viscosity solutions and some approximation arguments, which I barely will have any time. Okay. If I get into those bushes, which are really not small bushes, then I will never see the end of the tunnel. Okay. So it's a conscious choice that I have to make. Okay. So now U is C1 alpha. Well, in that case, in the divergence form case, you saw that once it is C1 alpha, because the nonlinearity is in the gradient, you can bootstrap. But here you cannot, because the nonlinearity is in the Hessian. So that makes the analysis of the non-divergent structure significantly harder than its divergence form counterpart. So you cannot bootstrap. So this is the bottleneck of this theory. And in fact, in 2007 onward, there are examples of Nadirashvili and Bedov that says that for dimension n bigger than or equal to 5, there are C1 alpha viscosity solutions, which Adimurti explained, to f of d square u equals to 0, and f is smooth. So what do you know about linear elliptic theory? Linear elliptic theory, coefficient smooth means the solutions are smooth. That doesn't appear in this kind of nonlinear equations. Okay, so this is kind of the limitation of this approach, and the examples of Nadirashvili and Brother in dimension bigger than equal to 5 tells you that generically you cannot go better than this. And this is the theory of Krylov and Safonov. So this is the Krylov-Safonov theory that if I have uniformly elliptic structure, whether I can get C alpha estimates which only depend on ellipticity and nothing else, okay, which will then imply that the solutions to the original fully nonlinear equations are C1 alpha. And Nadirashvili and Brother, what they did is that they got in dimension bigger than equal to 5, inspired by the theory of similar constructions for minimal surfaces, they were able to construct homogeneous C1 beta solutions for any beta bigger than 0, where this fully nonlinear operator has real analytic dependence on d square u. So it's a conjecture for n less than equal to 4, whether the solutions are even C2. Once it is C2 or C2 alpha, then you can bootstrap. Why? Because then f of d square u, so then it's a successive argument. If you knew that it is C2 alpha, then you can do better. Why? Because then f del ij of d square u, ue, ij equals to 0. If you know that u is C2 alpha, then this is C alpha. Further theory will give you that this is C2 alpha, which means that u is C3 alpha, because this happens for all directions. That means that this now becomes C1 alpha, this will become C3 alpha, so this will become C2 alpha, this will become C4 alpha, and so on. So then you can repeat. So if you cross C2, then you are smooth. Then it does not take into account the structure anymore. But you can never in general cross this waterline for generic solutions. Okay. So this is the best that you can get in this theory. For dimension 2, in the linear theory, you have better C1 alpha estimates, and that follows from the quasi-conformal theory. You can show that the gradient is k quasi-conformal depending on the ellipticity, and that is the theory of Lippmann, Burst, and Nirenberg. Then you know that B is C1 alpha. If B is C1 alpha, then U is C2 alpha. Then you can bootstrap. So n equals to 2, U is C infinity. It's F is C infinity. N equals to 3, 4, open. N bigger than equal to 5, counter example. So this is the state of the art. So in the first part of the lecture, what I will do is that if I just assume f to be fully nonlinear elliptic, I will prove that by the derivative equation, I will prove the C alpha estimate for this, which will imply that for the original f, the solutions are C1 alpha. Okay, and then I will tell you that if you have a concave structure or a convex structure, the Evans-Krylov theory will upgrade it to C2 alpha. But that is like assuming some other geometric condition on the fully nonlinearity in addition to uniformity. So that will be the next segment of the talk. And then I will try to describe another very beautiful idea of this Caffarelli. So I will assume everything in the smooth setting, okay? But then the thing is that what Adimurthy stated, which is one of Caffarelli's contribution, well, let me just come to that, okay?
So this counter example, that is capital F analytic or?
Yes, it is analytic. So that is why I am saying that it depends eventually, the further regularity depends on the geometric assumption. The concavity or convexity is a geometric assumption, but regularity is not. So this is the Krylov-Safonov. Krylov-Safonov. If Aij equals to 0, U is non-negative in B1, then supremum of U in B half is less than equal to constant, which only depends on ellipticity. So Aij is uniformly elliptic. And supremum of U, infimum of U over B half. And then similar to that, as in the divergence form theory, once you have a Harnack, this implies that if I take a sign changing solution, U is C alpha. So this is for a non-negative solution, this Harnack inequality, that the supremum, which is the infinity, is controlled by the infimum, which is the 0. But then by a similar argument as in the divergence form case, because then it does not differentiate anymore between the structure, you get that U is C alpha. So Harnack implies holder, kind of standard in the theory, which I explained already in my first lecture. I won't do it again. So the good chunk of my lecture would be focused on this. Now let's try to understand this more. As I said, if I have Aij, Uij equals to 0, by ellipticity, I have that d square u plus is comparable to d square u minus. But then, if I give you any u for which d square u plus is comparable to d square u minus, then I can always cook up an Aij. what I do is that I go into the coordinates of d square u that diagonalizes it, and then I can hook up the aij's which are diagonal so that some multiplication of that make it 0, because there will be a good positive chunk, there will be a good negative chunk. I multiply this. So what I will have is that I will have some set of positive eigenvalues, some set of negative eigenvalues, and I know that these some of these eigenvalues and some of these eigenvalues are comparable. So I will multiply it by with a proper constant point by point, and then I will get that the aij divided the trace is 0. Okay. So I take the aij's which are diagonal, which is some constant here, some other constant here, so as to make this whole sum 0 in the trace. And then if I come back to my original coordinate, I am able to get this aij. In the coordinates of d square u, it will be diagonal, but when I come back, I can at most have qualitatively at most bounded measures, right? And uniformly elliptic, but no better. Okay. So I'll focus a good part of the theory on this. Now, this is more of a point-wise information, but in the Banerjee's theory, the starting point was much easier because it's an integral equation, right? You have test functions, so you get Cacciopoli. But here you just have this information, which is the point-wise information. How do you go to a measured information, right? Point-wise to local or local to global. And this turns out is one of the great developments in the theory that allows to go from a point-wise information to a measured information, right? And that is the Alexandrov-Backelman-Pucci estimate that tells you that allows you to relate this non-divergent structure with an operator which has the divergence and the non-divergent structure at the same time, which is the Monge-Ampere operator, that of d square. Okay. So I will now describe the ABT. So ABT. So if U is non-negative, Aij, Uij is less than or equal to F in B1. Okay, well, non-negative on boundary. So Aij, Uij is less than or equal to F in B1. U is non-negative on boundary of B1. Okay, then the ABP estimate tells you that supremum of U minus over B1 is less than or equal to constant times that of C square U on the contact set of U minus, okay, raised to power 1 by n. Right? This is on the contact set, so the determinant has a sign. Okay. And how do you see that? And then once you use the determinant is like the product of the eigenvalues, and then if you use the trace determinant inequality, you can control it by the sum raised to power n. So then you can control it by the ellipticity. Sum is controlled by ellipticity by Aij, Uij. So therefore, Aij, Uij would only live on the set where you have convexity, which is to say that you can replace this by s plus 2n. Anyway, I will describe this, okay, as we go to this. So how do you prove it? Not much in the proof, except for the fact that Caffarelli made this big insight, which makes this theory more robust to be used for viscosity solutions. Okay, so here is the proof. I have this, okay, and this is the graph. Okay, so at this side is the boundary, and then suppose this is the minimum point, because this is the supremum of U minus. So how minimum I can get? So let this value be m. Now the diameter of this is like 4, right? 4, 2, whatever. Okay, it's a big number. So now what I do is that if I take a p in Rn such that norm of p is less than this m by 10 million, I don't care about the number, just 4 or 5 could do, but I'm just exaggerating it for the sake of it, that don't care about epsilon delta if you have to do this kind of maths. Okay. So now what I do is that I take a slope, I take a line, and then I slide this line till I hit the graph of U for the first time. Okay. Now my claim is that if I take a slope small enough compared to this side, I will always hit this point before I hit the boundary. Why? Because if I hit the slope, if I move this plane from infinity, moving plane method, if I were to hit the boundary for the first time, suppose I hit it here. Okay. And then if I follow the slope, the norm of P is less than m divided by a large quantity. If I follow this line, I can never reach the minimum because I'm dividing by the diameter of the domain. Clear? Okay. So therefore, the first touching point is to be inside. And how do you justify it? Well, you can justify it in a very easy way because if you have, I mean, just make this point 0 for an exaggeration. This is also -1 boundary of ball, but just translate it, make it 0. So therefore, the plane would look like P dot x, right? But then this is less than equal to norm of P times norm of x. But norm of x in a ball of size 1 is at most 1. And this value is less than m by 10 to the 5 or 10 by 4. So there is no way I can reach this point if I follow the slope. Okay. So therefore, these are all these slopes are the contact points of the graph. Okay. Right. All these slopes are contact points of the graph. And then what do you do? So therefore, what you have is the following: that the gradient. So the gradient of this B1, okay, gradient of U minus of B1, okay, it contains all slopes which are like order m, right? Because all such things are slopes here. So they are all sort of supporting planes to graph at some points of the other. Why? Because they will not touch the boundary point. Because if I follow the slope, as I said, I can never reach this minimum point. Okay. So this contains ball of radius m over 4. Okay. Clear? So therefore, what is the size of this? The size of this is m to the n up to a constant, which I don't care, and this will be less than equal to this. But if I use the change of variable formula, what is this? What is the image of this? This will be set of d square u over the set where u is touching this, over the contact set, because all such points are contact points. That is, what is the envelope? The envelope is that, let me exaggerate this picture a bit. The envelope is the largest convex function which is sitting below, and at every point where you can touch it by the line, by the characterization of convex function is the superqualified functions that are below, you get that they have to be the contact points of this. And at the points where it doesn't touch, in one dimension it is linear, right? But in higher dimensions it can sort of curve out. But there will be some segment where it is affine, so the delta of d square at that point is 0. Okay, it doesn't matter. So this is only important that these contact points, okay, and at this point you have delta of d square u. But what is delta of d square u? These are all convex points, right? Because there is a plane from below. The function is convex on these points, right? If there is a plane from below, at that point, all the curvatures are non-negative, right? So what is delta of d square u? This is like lambda 1 up to lambda n. But then lambda 1 to lambda n is less than equal to the largest lambda max to the n, and this will be less than equal to aij. This will be less than equal to, so lambda 1 to lambda n will be less than equal to up to a constant lambda 1 all the way up to lambda n whole power n. Agree? But by ellipticity, these are all positive. These are all non-negative. Why? Because at the touching points, all the curvatures are positive. So at these points, by ellipticity, I know that my aij, okay, is always between two positive constants. Okay, so therefore this is less than equal to aij uij to the n, and it is only touching at the point. Only the so now, and at non-negative points, this will be f to the n. But at all such points, f is positive, so I can replace it by f plus to the n. Clear? So this is the proof of ABT. So n to the n is controlled by this, and therefore, if I take 1 by nth root, m is less than equal to integral of u contact set of u. I mean, this is a bit of a misnomer, bad notation, because I'm really not taking the contact point of u, but u minus. Okay, u minus of u minus. Okay, because u minus is like the inverted picture. U minus is different, right? U minus is minus of main u comma 0. But I'm actually taking min of u comma 0, which is minus u minus. So this means okay. So that I don't flip the picture the other way around, because then the convexity will change in concavity, which is bad. Okay. So this is m to the n, f plus to the n, and then I get this one. So this is the proof of ABT. I will not tell you why the Monge-Ampere has both a divergence and a non-divergent structure at the same time, because when I do the Monge-Ampere in details, we will try to introspect more into the structure of that operator. That will be the lectures on Friday. Okay. So now, how do I apply it? The other ingredient that I need is the Calderon-Zigmund lemma. So what I have is that, suppose I have A, two measurable sets contained in okay, such that measure of A is less than delta times measure of Q1. Now I have the following condition that B covers A in density. That is such that, and if for a Q, if given Q, this could be any Q, such that A intersection Q over Q is bigger than delta, then 2 times the Q is contained in B. So this is the condition. Suppose star holds. Then what is the conclusion? The conclusion is that not only A is covered by B, but A is covered by B in density in a quantitative way, which is expressed by this. Then measure of A is less than delta times measure of B. Okay, this is another key ingredient that we will use. You see, you know very well that in the singular integral theory, this is kind of the key lemma, right? Well, there are many other things, but cancellations are important, but we don't see this covering lemma has a very pivotal role. So now how do I prove it? Okay, so what I do is that, okay, so I start with a Q1, okay, and this is my A set. I mean, it's not like it's dimension 2, but this is the best I can draw. Okay, so but my procedure is the following. So I keep little space here, last space here, little space here, last space here. What I do is that given any cube, I first diagonally divide it into 2n cubes. And if it 1 cube, the density crosses delta, I stop. And if the density is below delta, I keep subdividing. Okay, so therefore, at this point, the density is crossing this delta, right? Because this is the A. First step, I subdivide. Why? Because measure of A is less than delta times measure of Q1. So the first step I will subdivide. But now you see, here the density is large, here the density is large, but in this case the density is feeble. So these two cubes I further subdivide. And then again I keep doing this whole process. Okay? So if at any next level, so these I keep as it is, this I further subdivide. Okay? And these also I keep on sort of subdividing because I mean I can make this picture more tight so that there is something more. Okay, so some cubes I have to subdivide, some cubes I don't have to subdivide. So then what do I get? I get a chain of disjoint dyadic cubes. So I get that there exists these Qj such that A intersection Qj over Qj is bigger than delta, right? But then by the Lebesgue differentiation theorem, these Qj's have to cover A in density, right? So therefore, up to the set of measure 0 by the Lebesgue differentiation theorem, because every point has to be a point of one density. So I have that A is contained in union of Qj modulo a set of measure 0, right? Now, each of these cubes have come from a parent which has been subdivided, right? Each of these cubes, why did this cube appear? Because the parent was subdivided. And why was the parent subdivided? Because there the density was less than delta. So I make use of this fact. So this is covered. If this is covered by this, so this is also covered by the parent. So I put 2q or the parent, call it q tilde. Okay. So now q tilde was subdivided, right? So A is covered by this, and q tilde was subdivided. So measure of A. By first, I will write this. This is nothing. I'm not using anything. Measure of 2q. This is just to say that there is a parent. But each of these Qj's, the fact that this it came from a parent which was subdivided, it means that on this set the density had fallen less than delta. So then this is less than equal to delta times the measure of Qj's. But each of the 2 Qj's are covered in B. So now I use the second condition. The 2q is covered in B. Right? And so if I use this, so then I can say that this is less than delta times the measure of. So what I do, of course, there will be repetition. So when I am at these cubes, these are all disjoint, right? Because there could be sort of like so this could be my selection of cubes. But when I go to the parent, right? So this and this are the same parent. So in this sum, I eliminate all the overlapping ones, okay? So that I have the disjoint ones, and so I don't keep any repetition. So two sons can have the same father, right? So when I use this, and then when I sum this, this is less than measure of B. So therefore, a quantitative information that if you have something that covers the other set in density, it translates into a statement like this. And this is another sort of key tool that will be needed in the proof of the Krylov-Safonov Harnack. So now, with all this technical preparation, let's get to the proof. Okay. Okay, so what I'll do is the following. I'll do that if u, so aij, uij, I will write as L of u. Okay, first to save some work. Okay, so the proof will go in 2 steps of the Krylov-Safonov Harnack inequality. One, if u is non-negative, Lu is less than equal to 0. If u of 0 is less than equal to 1, then u is in L epsilon. What is this? This is like a super mean value, the super mean value property, right? If you have a subsolution, super harmonic function, u of 0 is bigger than equal to delta of u over v, except for the fact that here you have an L epsilon norm. Okay, this is the super mean value property. Everything is non-negative. Okay, but if u of 0 is less than equal to 1, this means that this integral is controlled. But here I am doing the same thing, but except that I cannot take L1, I have to stop at some L epsilon. Okay. So this is the first thing. So this is like a generalization of the super mean value inequality. And the second thing that I show is that if u is non-negative, u is a subsolution such that u is in L epsilon, then u is bounded. U is in L infinity. So if I combine this, what do I get? I get that u of 0 is bigger than equal to u epsilon over v half. And this will be bigger than supremum of u over p half. So if I have a solution, that is, I have that this is equal to 0 and this is equal to 0. Okay, and that is what. So u0 is controlling u b half, but then I can take this 0 conveniently. I can take this 0 to be the infimum, right? Because I'm in a big ball, and in half the ball, I can move my 0 around by translation. That does not fit in the structure. So this is like the infimum. So all are actually constants. Okay. So supremum is controlled by the infimum, that is Harnack. So I'm able to convince you that if I go do these 2 steps, then I'm done with the proof of Harnack. One Harnack is there, then hold it forward. Okay. So now, using the APP that is over there, well, remember it in whichever way you want to. First, let me show the following. Okay, and then I will improve it. The first is the point measure lemma. Point measure lemma is the following, that if u is non-negative, L of u is less than equal to 0. If u of 0 equals to 1, then the set where u crosses 2 is less than equal to b1. U crosses 2 intersection b1 is less than equal to theta. Theta times, and the measure of unit ball is say 1. Okay. The important thing is theta, where theta is strictly less than 1 and bigger than equal to 3. Okay. So how do you prove it using APP? So what is this telling? So if I have a large constant, let me tell you that this is sort of quantifying the super harmonicity or the super solution property. So what is it? So u of 0 equals to 1. So this is the graph of u. And if I take a large n somewhere over here, which is very large, okay, such that this set, the graph of u is over this set, okay, very large. Suppose this value is 2, this value is 1 or less than equal to 1. This is 1 level, this is 2 level. I'm just exaggerating it for the sake of it so that I can explain it by the picture. So if this set is too large, right, that means that this theta is very close to 1. That means that I have a very narrow region that I can go from 2 to 1. Then I have this much of time to go from 2 to 1 if this set is very large. But what does that mean? This means that you have a net of very high convexity. But if you have a super solution, the negative part of the matrix should win over the positive part. So it should be more concave and less convex. And therefore, this measure extended lemma has a lot of hidden geometric property. It gives you a control on the convexity of a super solution as it should. Okay, so how do I prove it? So I have this graph. This is u0 equals to 1. And then what I do is that I slide it down by a quadratic polynomial. Okay, I slide it down by quadratic polynomial so that 1 becomes minus 1. So what I do is that I take a function phi, which is like 2 times mod of x square minus 1. Okay, if I take this, so then if I take now u plus phi, so u of 0 is 1, phi of 0 is minus 2. So if I take u plus phi, call this my v, so then what happens? Then the new picture will be that this value has become minus 1. So this is the graph of v. And by the time it escapes v1, phi is positive, u is positive, so at minus 1 comma 1, it has to escape. But at the center, this is highly negative, so that with this function phi, I'm able to drag down this. And now what I do is that I apply the APP to this. Okay? If I apply the APP to this is right in the setting, right? By the boundary, by the time it reaches the boundary, it becomes positive, and otherwise it's negative, right? At least in this region. So I'm able to capture. So for this, I get that supremum of B minus, but it could be positive somewhere else because I have no understanding of it could be like a very large. So there could be some portions where it's large. But at least I know that at the center, it is minus 1. So the minimum, so the supremum of B minus is at least 1. Because it is sliding all the way to minus 1. Okay, so supremum of B minus is bigger than or equal to 1, because at least at a point I could slide it down. This will be less than or equal to when I apply the operator to it. But then L of u is less than or equal to 0. L of phi is controlled by a constant, right? Because here I can evaluate it. It's a nice smooth function and AIJs are bounded, right? So I can bound it from above. So this will be C times the measure of the contact set. So the measure of the set B minus, right? Clear? So what am I doing? I'm just applying this to C times L of B whole n 1 over n contact set of minus B minus. Okay, this is actually the contact set minus B minus. But LB is what? L of u is less than or equal to 0. So this is less than or equal to L of phi, but L of phi is controlled because u is smooth, phi is smooth, right? So Aij phi ij is controlled by lambda times d square phi, and d square phi is at most 2 or 5 or 10, whatever, I don't care. Okay, so this is controlled by a constant. So when I recover it, this is less than or equal to C times the measure of the contact set, and this is bigger than or equal to 1, right? So if I change this inequality, 1 is less than or equal to this. But on the set where this happens, on this set, we have to have that v is less than 0, right? Otherwise, this doesn't make any sense, right? And v less than 0 means u less than minus 5, right? So if I go back, and what is minus 5? What is the maximum value of minus 5? Is minus of minus 2, which is 2. So this is 2. So for phi, 2 of mod x square minus 1, minus 5 cannot be larger than 2, right? At the center, it is maximized. Minus 5 is maximized. Clear? So therefore, what I get is that u less than 2 instead is bigger than or equal to 1 by c, which is a good chunk, right? So there is a c, which this c, as in the ABP, only depends on ellipticity and the dimension, and this is bigger than or equal to good chunk. So therefore, the set u bigger than 2 is less than 1 minus 1 by c, and this is your theta. Okay? Clear? So if this set is large, which the ABP provides, the other set is small. That's all. I know these lectures are fast, but I have to do justice to this event, right? So now I want to localize it. So what I now do is that I state a more general one where I can localize this thing a little bit more, which is to say that this is the localized, better refinement of this lemma, more defined lemma. So this was just to give the idea how it happens, but in practice, we have to modify this phi a bit because we have to localize the estimate here and there so that we can make it fall in the setting of Calderon-Zigman lemma. Okay, the lemma that I had. So what do I do? So what I do is the following, that if to non-negative LU is less than equal to 0, and in Q4 large cubes, okay, Q4 before I keep on using it interchangeably, okay, but in dimension 1 they all match because this is where I can draw the picture, okay, and suppose that infimum of U over Q3 is less than equal to 1. That is U of 0 less than equal to 1 can now vary in that cell, okay, somewhere, but it is far from, so I can always translate it and make it my U0. And then what I want to claim is that there exists theta which only depends on ellipticity, lambda and n, such that U, and there exists m, theta and m. So I cannot take any more 2. In that lemma I could take 2 as m, but I have to now take a large N of m such that the set where U is bigger than m intersection Q1 is less than theta times measure of Q1. So from B1 I make Q1. Okay. So this lemma, for instance, it's in B1. So whatever it is. Okay. So this is in B1, but this I can make it Q1. Okay. So what do I do? Because they are all contained in one another up to a dimensional constant, right? Cubes and balls are all comparable to one another. So what do I do? Well, now I do not have the same luxury because now my infimum shifts. So what I do is the following. So this is minus 4, 4. This is minus 3, 3. Okay? And then this is minus 1, 1. So what I do is that I slide this cube so that by the time it reaches minus 3, what is the most dramatic situation? The infimum is located far at the boundary, right? Infimum is located at the boundary point, right? Here or here. So I slide a function which is like minus C1 minus C2 r to the minus alpha. So that this becomes like this, okay? So I slide this function, and by the time it reaches minus 1, I cover it with a cube like this, with a quadratic paraboloid like this. So in this region, when it reaches minus 1, 1 and 1, I extend it in a quadratic manner, okay? And then I sort of, by symmetry, I sort of put it here. So how much I need to slide? So I have to go from 1 to minus 1 so that this length will be 2. This length will be 2. So that, and this length is even more. So therefore, by the time I reach here, I would know that if I call this to be my phi, then I would know that U plus phi, there exists some x in Q3 such that U plus phi is less than minus 1. Right? Because this value is minus 2, the infima. Where is the lemma? Where is my lemma?
You erased it.
Okay, so the lemma was that the infimum of U in Q3 is less than equal to 1. Okay, so if I slide it by this phi, then this will fall to minus 2. So minus 1, right? Because this is minus 2, so U plus phi, there will be a point where U plus phi is less than minus 1. Why am I needing to do it? Because I don't know where my U0 is. So I have to sort of adjust this function suitably so that my contact points stay over here, because this is the convex part. This is the bad part. And this is like a concave function, right? In dimension 1, yes. But in other dimensions, so here on this, on the radial direction, there is concavity. But there are other directions too. So in higher dimension, the situation is more complicated. Okay? There are these directions too. So let's evaluate this. How much of alpha do I need? Because in one dimension it's okay, but not all one dimensional things generalize. Because on this direction there is good concavity, but on these directions there could be some convexity which could sort of be killing. So what I do is that because I know that this R, what is R? R is like mod x to the minus alpha with an adjusted center. But because it is rotationally invariant, I just compute the eigenvalues at 1, 0, 0, 0. And then I know that the eigenvalues are the same because this is a radial function. So it is rotationally invariant. So I only need to compute d square phi at this point. So now let's do the computation. So this is my function phi. Phi I is 1. So phi 1 is minus alpha mod x to the minus alpha minus 2 x1. And if I do phi I, this is x1. Right? And then what is phi ij? Phi ij is, I just do phi ii, okay? Because in the end I will phi ii is, or phi ij, let me do phi ij is minus alpha mod x minus alpha minus 2 del ij and minus alpha times minus alpha minus 2, okay, times mod x to the minus alpha minus 4, and I can sort of remove, then I can remove all this part because at this point the norm is 1, okay, and then what is that anyhow, let me still continue. So this would be xi xj, and now I put the values. I know that the point that I am evaluating is 1 0 0 0 0. What you see is that at this point the eigenvalues are the following, right? At x1. So when I do del ij phi 1 1, this is minus alpha, right? This is minus alpha, and but then there is a positive part which is minus alpha minus 2, and this part is positive. Alpha times alpha plus 2, and then there is a minus alpha. So whatever it is, the phi 1 1 is alpha times alpha minus 2, alpha plus 2 minus alpha. So if alpha is large, this is like order alpha square. So the positive eigenvalue is comparable to order alpha square for mod x to the minus alpha. So for minus mod x to the minus alpha, it will be a negative eigenvalue. And what are the other eigenvalues? Other eigenvalues would just be all these minus alpha, right? So all these are minus alpha. So therefore, if I choose alpha large enough compared to ellipticity, because then if I take aij or phi ij, this will be bigger than equal. Phi ij is this. Well, this is different phi, so let's call it a different name. Let's call it psi. Because I ended up by mistake calling it phi because it's the minus of that. Okay. So what is aij? So this is bigger than equal to this eigenvalue, little lambda times alpha square minus n minus 1 times capital lambda times alpha. If I take, so now lambda and lambda are comparable to one another by ellipticity. So if I take alpha large, then I can produce a sub solution for this. That means I can produce a super solution for this. So the one dimensional picture is misleading, as I said, because in the one dimensional picture, you could only see for this function, the concavity, because it will be the minus of this, right? Because what is this? This function is just the inverted one, right? This is this means this is this. But then there are these other directions where the eigenvalues change. But this is quadratic, this is linear. So therefore, if I am able to take alpha large enough, then I am in business. This is exactly the same proof that you have for the Hopf lemma. In one direction, it is order alpha square. All other directions is alpha. Okay. So therefore, I am winning. So now I know that in a very uniform way, I can reach up to here. So now I apply to u plus I. So I apply that estimate to u plus I. So therefore, if I take b to be u plus psi, what is u plus psi? So that by the time I drag here, so let's change it to psi. Okay, because I have changed phi and psi. So u plus psi, I know that this is less than minus 1 at some x in q3. Right? So therefore, if I take supremum of b minus, the ABB applied to this will be again bigger than 1. And then if I look at this integral would only be localized on this q1, because this is the set where you have some positive convexity, right? Because this is the only set where you are having a subsolution, potentially a subsolution property. Because at other cases, it is a super solution. Make sense? Because for this function, this is bigger than equal to 0, but for the negative function, it is less than equal to 0, because this is the inverted one. So this picture is the one for which I computed the eigenvalues. But if I flip it, this is the one that I have there, is what I get. I know that L of u is less than equal to 0. So at all points which are here and here, I know that L of u plus phi is less than psi is less than equal to 0. So if at all there is a positive part where Lu plus phi is bigger than 0, that has to be concentrated here. So again, I have the same estimates that it is less than equal to 3 times the measure of the contact set. But again, the measure of the contact set is where, so on gamma p minus, you have to have that p is less than 0, which is the same as saying that u is less than minus psi. But then this is controlled by a dimensional some large m, right? So it depends on how much of the alpha that I take, that I need to go from this value to this value. And this is already a dimensional quantity, right? I just need to hook up enough super solution property so that I bend it enough. So by the time I reach here, it is still dimensional, because the distance between 3 and 1 is kind of uniform, right? It's not infinite. So how much can this function go? You calculate it, right? This cannot go much. And here I can control it by a quadratic paraboloid. So it can only dip down another 2, which is 2 of minus 2. So at most it is like up to here m and here m plus 2. So that is my new m, which is over here. Okay? Here, so this is what you get. So now, so therefore, so this is at most m plus m minus m. So therefore, again you get that the set when u is less than m is less than equal to is bigger than equal to 1 by c. Right? Because this c you take it here. So this is the set. So the set of this contact point is where v has to be less than 0. V less than 0 means u less than minus sign, but this has an upper bound. Minus sign means what? You invert this function the other way. This will have a maximum large value, which is quite dimensional, universal. So u less than m is big chunk. So therefore, and where does it live? This only lives in Q1. So this is intersection Q1 because this is the only set where you can expect a convexity property where you can have a tangent line from below. At other points, you have the super solution property, so that cannot be. Okay. Therefore, again you have that there exists m such that q bigger than m is less than equal to theta. That's the measure of Q1. Now these contact points are very special. What happens at these contact points? These are the points where not only you get a control on u, but you also get a control on du. Why? Because there is a tangent plane from below. These are the contact points. The contact point, there is a tangent plane from below. So at all these points, you have a good control on du. And you also have a control on d square u from below. Because at these contact points, on gamma b minus, these contact points are so special that on these points you have that d square of u plus psi is bigger than equal to 0 because there is a tangent plane from below. So that means that d square of u is bigger than minus d square of psi. So that means that on these contact points, the negative part of the Hessian, so therefore you get that d square u minus is bounded. Right? Because it is bounded by the largest phi, right? And d square phi is psi is bounded. Why? Because psi is a smooth function like this. It's a universal function that you have to construct for this situation. But now, what does ellipticity tell you? If because I have that aij, uij, suppose I do it for solution, aij, uij equals to 0, so d square u plus is comparable to d square u minus. So at this point, if you are able to control d square u minus, you may as well get a good control on d square u plus. So now, the epsilon estimate that I will do using these contact points, not only they will be valid for u, they will also be valid for du as well as d square u. So in the end of my proof, I will be able to show that if I have aij, uij equals to 0, then d square u is in L epsilon, where epsilon is a number, universal number, which only depends on dimension and the ellipticity. And the fact that d square u is in L epsilon was first observed by Fangua-Lin and also Craigie once. Okay. So when I run this proof, so that, but now I will stick to the proof of now using this. So now I will state that, and then I'll just take this lemma once more, okay? And then I will just take the refinement of this. So the refinement is over here that I just proved. Lemma 2, lemma A says that if u is non-negative, Lu is less than equal to 0 in Q4, infimum of u of Q3 is less than equal to 1, then there exists u m intersection Q1 is less than equal to theta times measure of Q1, which is 1, but I will just exaggerate it and still put this number even though it's 1 to say that this is where I am sort of looking at the super level set where m and theta are universal and theta is between 0 and 1. The important thing is that this theta is strictly less than 1, which is what will this will be my delta. So now I show the following. So for the n that I got, now I will show that u bigger than m to the k is less than equal to theta to the k. This is for all k. and this will give me an epsilon. Okay. So first let's prove it. Then it's a real analysis argument because this is the geometric decay. This theta is strictly less than 1. So it tells you that the super levels are decaying at a geometric rate, and that is nothing. Why? Because if you want to do u bigger than t, any t is like m to the k, right? If I put it, so then I get that u less than t in the sense that you can trap it between m to the k plus 1 and m to the k. So this will be like less than equal to theta to the k, but k is like log of, so this k will be like log mt. So you put it like, so this is like theta log mt, and then from basic logarithm that you know from high school algebra, this is nothing but t lm theta. And this is a negative number. Why? Because theta is less than 1. So this is your minus epsilon. So therefore, what you get is that if I, from this inequality, you get that u less t is less than t to the minus epsilon. So that means that n is in u delta for all delta less than epsilon. Right? Because now use the layer cake representation. How do I do it? Taking a lot of time. Okay. So now how do I do it? So the way I do it is the following. That suppose, okay, so I write ak to be u bigger than m to the k. What I want to show is that measure of ak is less than or equal to theta times measure of ak minus 1. And what is the way to show it? I repeat the Calderon-Zimmermann lemma. I will show that if there exists q such that A intersection q, measure of q is bigger than or equal to theta, then this should imply that 2 times q is contained in ak minus 1. So this will be my A, this will be my B. Then the conclusion of the Calderon-Zimmermann lemma will give me that measure of AK strictly decreases in a geometric way compared to the measure of this, which is this theta. Because if I iterate this exactly gives me theta to the k, right? If I just, then AK is less than theta AK minus 2, so then theta square. So it sort of increases, right? So how do I do it? Well, suppose I have a cube where this density is crossed somewhere. Then I zoom in, translate that point, because the ellipticity stays invariant by zooming in, right? It's a scale invariant quantity. So that cube, I can think of it as Q1. Okay? So I can think of that cube as Q1, and where, so without loss of generality, because the ellipticity is scaling invariant, this Q is Q1, where this density is crossed. Okay? Now what I do is that I take B to be U over mk minus 1. Okay. So what does that give me? This gives me that V solves Aij with a new Aij, which has the same elliptic property, because Aij of R of x plus the translation, but which has the same ellipticity character, times Bij equals to 0 or less than equal to 0, such that B bigger than M is bigger than equal to theta, right? Because this statement for V becomes that V bigger than M is bigger than equal to theta, right? And then from what I prove that lemma A, so that means that the conclusion of this lemma is violated, so the hypothesis itself is wrong. So that means that the infimum of U in Q3 has to be bigger than 1. Is it clear? Because the set where B is bigger than M is the same as U over mk minus 1 is bigger than M, which is the same as U is bigger than M to the k. So I have condensed a lot of information into one. So this set is the same as looking at this set, where this hypothesis is violated. So therefore, if I apply that lemma, I will get that infimum of B in Q3 is bigger than equal to 1. So that means that U is original U is bigger than mk minus 1 into Q. If I go back, right? Which means what? So this means that 2Q is contained in AK minus 1, because this is precisely the super level set. So I have been able to run my Calderon-Zygmunt hypothesis on this based on the scaled estimate in the first lemma, and I get that these AKs deteriorate geometrically. So this proves the ellipsoid. And so now I go to the second part, which is if U is a subsolution which is an ellipsilon, why is U bounded? Very slow. So now the thing is that I solved sub-solution estimate. So U non-negative. This is better actually. I wish I listened to you. Maybe I took a different job by mistake. LU bigger than equal to 0. If U is an ellipsilon, like U is bounded. I just need to show that U0 is bounded because then I can localize the estimate, right? Like in behalf. Okay. So how do you do it? Unfortunately, I could not tell you that that measured uniform lemma is the inverted form of the De Giorgi's measured uniform lemma. Okay. It's unfortunate, but the thing is that I'm running short on time. It's already 5. I have 30 more minutes. Okay, so I have to wrap up. So how do I do it? Suppose I have this situation. I want to bound U of 0. Now it will take us to the argument of the first lecture that I had in the morning, where I proved the Carlson estimate. Suppose U of 0 is very large. I want to get a bound on this. Suppose U of 0 equals to M. Then I want to show that there exists delta universal independent of M such that in some Q M to the minus delta, which the size of the cube is very small compared to delta around 0, you have to have that U is supremum of U is bigger than 1 plus delta M. Okay? And how do I show this? So you see, like, I mean, you have a doubling, but you have a doubling in a region which sort of in a size of cube, which decays also geometrically. Okay? So why is it so? So I will sort of just scale the picture up and down, okay, for you. So U0. Of course, I know by the strong maximum principle of solution, so it cannot be the maximum, so there is some value that is up. So I just need to quantify this delta. That is what my job is. Okay. So this is M, this is 0, this value is M, this is U0, and this is say delta. So U doesn't go beyond delta. So this is like 1 plus delta of M. Right? Now what I do is that, so this distance is M, this is 1 plus delta M, so this is like delta M. So what I do is that I scale this to 1 and I invert this picture. Okay? So if I scale this to 1 and invert this picture, this is more like looking at W, which is 1 plus delta M minus of U divided by delta of M. Okay? Now I want to, so what I will show is that if this, what I will show is the following, that if this delta, if U doesn't cross this delta, if U doesn't cross this delta, I will show that the set where U is bigger than M by 2 and the set where U is less than M by 2, both are less than half the measure of Qm to the minus delta. And that cannot be, because these two are complementary sets, they have to fill this cube. How? Now the set where U is bigger than M by 2 decays like M to the minus epsilon. This is the ellipsilon estimate that is my hypothesis, right? U is an ellipsilon. I only need weak ellipsilon. And then what I do is that I choose a delta smaller than epsilon such that this is equal to 1 by 4 M to the minus delta. So it has fallen less than even 1 by 4. Okay, the size of the set. N. Okay, because you multiply all dimensions, right? I am pretending as if I am doing everything in dimension 1, but this gets multiplied. So you choose delta to be very small. Okay, so that this is what happens. M is larger than 1, which I want to bound. Now, so this is fine, this is nothing, this is not using the PD, but now the inverted picture becomes a the inverted picture becomes a super solution. So if I scale this, what the inverted picture is that this is my level m by 2, right? So the set where u is less than m by 2 is the same as the set where w is bigger than delta to the minus 1. Why? Because if u is less than m by 2, then what I get is that 1 plus delta m minus u by delta m is delta. So this is bigger than, if u is less than m by 2, so this is at most m by 2. So this is bigger than 1 plus delta m minus m by 2 divided by delta m. And then the thing is that m by 2 gives, okay? So this is equal to, and m by 2 plus delta m. Delta is very small, so I ignore it. So it is bigger than equal to m by 2, and behind I have delta m. And I cancel. So therefore, this is bigger than equal to 1 by 2 delta. Well, how do I care? If it is 2 delta or 1 delta, I choose my delta. Okay. Important thing is that there is a delta, right? So the set where u is less than, because what I'm doing is that I'm zooming this to 1, so this distance becomes very far. If I flip the graph, which is what I'm doing. I'm flipping the graph, and I'm making this scale to be 1, dividing by delta m. So then this distance, although it is in the original picture at a distance m by 2, but in the rescale picture, it is at a distance which is very, very large, like 1 by delta. And now, what do I have? So what I have is that, so therefore, the set where you, again, let me write, m by 2 is the same as where w is less than, bigger than delta inverse, okay? And now what is W0? W0 is 1. So if I apply the L epsilon estimate, U is, what is W? W is a non-negative super solution. Why? Because U is a subsolution, so W is a super solution. Constants are annihilators, they are in the kernel of the operator. So this is what you have. So L of W is non-negative super solution. So the set where W is bigger than, in the rescale picture, W is bigger than delta inverse is less than equal to delta to the epsilon, because I am now using the L epsilon estimate that I have already established. What did I establish? If I have a non-negative super solution which is 1, then W is in L epsilon, right? Because the infimum is what? Less than equal to 1, because there is a value where it is 1, delta to the epsilon times the measure of the set, which is Q of n to the minus delta. Let's not call it delta, let's call it gamma. Okay, well, I have used a bad dot delta. So what I would do is that I will call this gamma. So what is gamma? Gamma is less than epsilon, such that m to the minus epsilon is like 1 by 4 m to the minus gamma n. So this delta and this gamma should not be confused. Okay. So I can always find a gamma less because m is bigger than 1. Okay. So therefore, what I have shown, this set and this set are both less than half the measure of this narrow q, which depends on how much the value of q of 0 is, and that cannot be. So that means what? This delta has to be something significantly large. There is a good delta which is universal, so that in this cube, u is bigger than 1 plus delta m. So now let me repeat this argument. So what I have is the following. I have here u of 0 is m. And then I have, there exists some x1 such that in this narrow cube, such that x1 minus 0, I'm purposely writing it this way because then I will repeat the points, okay, is less than what? Less than m to some minus gamma, such that u of x1 is bigger than 1 plus delta m. Yeah, so x1 is say somewhere over here. Now at x1, if this value is bigger than this, then again in a portion, if I repeat this argument at x1, there exists some x2 such that now the new value is what? 1 plus delta m, so that this is less than 1 plus delta m to the minus gamma, such that u of x2 is less than 1 plus delta square times the 1 plus delta times the previous value, which is 1 plus delta times 1 plus delta times m, which is 1 plus delta square m. Okay. Clear? So this is what I have, and now I repeat. So in the again I go to x2, which is somewhere in this narrow cube over here. Then again I can find an x3, and I can repeat the procedure. If I go one step at a time, I get that there exists xk such that xk minus 1 is less than equal to, let me see the pattern, it is like 1 plus delta to the k or k minus 1. Don't bother about k or k minus 1. So these are very shallow details. Okay, this is not the way we think. You put it k minus 1 if you want, it makes no difference to the final output. Minus gamma. Such that u of xk is bigger than 1 plus delta to the k m. Now, I want to calculate what is xk, norm of xk. So how far can this xk go as k goes to infinity? So this is my minus 1, sorry, this is my minus 1 and this is my plus 1. So these are the way the points are going. I want to say how much it can slide. What is the worst case scenario? The best case scenario is that these points are oscillating here and here. Right? The worst case scenario is that these points can slide too much to the right. So therefore, that I will stop by my m. Xk is less than equal to xk minus 1 plus xk minus 1 minus xk minus 2 and so on. And how are these distances growing? Like this. This is like summation 1 plus delta to the minus k gamma m to the minus gamma. And I can bound it uniformly in k from 1 to infinity. So now if I take this delta is universal, now if I take m to be very large, then I can make this norm xk less than half. So if I have that at a certain point the value process m, then there exists some x infinity such that x infinity is less than half, less than equal to half, because each of these xk's are less than equal to half, then up to a subsequence, not even a subsequence, up to the entire sequence, because this is a Cauchy sequence, xk goes to some x infinity such that u of x infinity is equal to infinity, because at every case there is a good chance that it is increasing than the previous value. If I put k equals to infinity here, I get that at this point ux infinity has to be infinity, and that cannot be. So there is a point in half the set where it becomes infinity if I assume that u of 0 is a big m, because this m quantifies for me how much I need to slide to the right. Slide to the right or slide to the left. This is left, this is right. So therefore, there exists a universal m such that u of 0 is less than n, so u is bounded. So if this gives me Harnack, right? If I have a super solution, infimum of u of the super solution is less than 1, then u is an epsilon, and then if I have a subsolution, positive subsolution such that which is an epsilon, that is bounded. So if I take it to a solution, I will have that supremum of u is controlled by infimum of u, right? By that string of inequalities that I described in the beginning. So this finishes the proof of Krylov-Safonov Harnack that gives you Helder. Okay. So now let me sort of write further outcomes of it. Okay. And as I said, this for my original fully nonlinear operator gives me C1 alpha, right? Now what can I say more? Now in the second part where I assume f to be concave, like the Monod-Ampere operator raised to a certain right power, conformal power which is 1 over n. So okay, f is concave. In addition to uniformity. First what I know is that, let me write this way, okay? This is much easier to write instead of del f by del I. So I write this because that is even a very bad notation. So d square u I equals to 0. So f is a solution to f of d square u equals to 0. Right? So this is what happens. Now, in order to get C2 estimates, I should derivate this equation further, right? What do? I differentiate differentiate it again. So once I differentiate this gives me Fij d square u of uee ij. So I take the derivative and I put it inside. So I'm just caring about a priori estimates, okay? And then what is the next thing that you have? The next thing is that you differentiate the structure. If you differentiate the structure, what you get is Fij Lm, two derivatives, and then d square u ueij uelm, and this is 0. Now this has a sign. This is a quadratic form for f concave, which is applied to these vectors, right? This is a quadratic form applied to vectors in the right dimensional spaces, right? In the space Rn square, okay? And therefore, if f is concave, then this has a sign. This is less than equal to 0, this part. But if the sum has to be equal to 0, this also has to have a sign. If this plus this is equal to 0, this is less than equal to 0, then this better be bigger than equal to 0. So what I have is that f of d square u ueij is bigger than equal to 0. So pure second derivatives are subsolutions. right? Clear? Pure second derivatives are subsolutions. Clear? And this uses concavity in a very, very crucial way. So then what do I have? Then I can apply the L epsilon estimate, right? So this is a subsolution which is in L epsilon, hence UEE plus and UEE minus are bounded, right? Because I have told you that if I have Aij, Uij equals to 0, then U is in L epsilon. D square U is in L epsilon, right? So therefore UEE plus and UEE minus supremum over B half is less than equal to UEE L epsilon over B2. But UE, because of this, as I said, I just made a remark, right? Whenever I'm doing the Calderon-Widman's lemma, it is not only valid for U, it is valid for DU and D square U. So this gives me that this is already bounded, right? So therefore, UE is bounded because UE plus and UE minus. So, well, sorry, not UE. So UE plus is bounded, right? If UE is a subsolution, UE plus is a subsolution, right? And UE plus is bounded. This happens for all pure second derivatives. I'm sorry, it's a bit premature that I wrote the other one, but this will follow. So this means that D square U plus is bounded. But since f of D square U equals to 0, D square U plus is comparable to D square U minus. And I have shown that D square U plus is bounded by this argument, so D square U minus is also a priori bounded, all by the L infinity norm of U. Right? So I have proved C11. And now I want to upgrade this C11 to C2 alpha. So I know that D square U is bounded, and now how do I get hold of the oscillation of U? Okay. So unfortunately, the way it is going, I don't think I can give a simplification of the original proof of Evans and Krylov that has been recently done by Caffarelli and Silvestre. I will try to postpone it to a later one on Friday when I do the Monjam. Okay. If I get some time, then I will do that trivia. So for now, in those 10 or 15 minutes, let me just give you the proof of the Evans-Krylov theorem. Okay. So I know that if I have a concave structure, D square U is bounded. I want to now prove that D square U is C alpha. How do I do it? It's a very geometric argument. So by multiplying by a right constant, okay, I can assume that diameter of D square U equals to 1. Now, in order to show, therefore, to show D square U is in C alpha, it is enough to show that there exists a K naught universal integer such that diameter of D square U over B1. Okay, I want to show that there exists some K naught integer universal so that if I take a dyadic ball of size, if I go further, if I divide it only K naught number of times, that is such that diameter of D square of U over B2 to the minus K naught, I will show that there exists a K naught where K naught is sufficiently large but not very large. K naught is controlled from above by ellipticity and the concavity character. Okay, then at this point the diameter has to fall less than half. That is from B1 to a certain scale B lambda less than 1, the diameter is falling less than half. If I now repeat this argument, I get that D square U lies in a smaller and smaller set if I make the ball shrink and shrink. So that is C alpha, right? This is like the oscillation decay. Here the oscillation is like comparable to 1. Now here I have decreased the oscillation, which is the diameter of this set, right? So if I show this, then I get that D square U is in C alpha the same way. If oscillation decays, U is C alpha that I showed. Now the same argument is there, right? Except that there the oscillation was falling in B half. Now the oscillation, for the oscillation to fall, you have to wait some K naught number of times. In fact, the new argument of Caffarelli and Silvestre only requires this to be B half. But this is a much more recent thing back in 2010. Well, 2010 for the point of view of research is quite recent, right? It's not. But anyway, I don't have time for this because I have just 4 minutes, 10 minutes. So I will just give you the proof of that. Okay, so now here is the set. So here is the D square of U of B1. This is the image. Okay, now what I do is that I cover it with two scale balls. One is the epsilon ball. I cover the image by epsilon balls. I make my epsilon a bit bigger, say sometimes, but this is what it is. So these are epsilon balls. So number of balls that I will require will be like epsilon to the n to the 4, right? Not more than that, right? Whatever it is, I don't care. Epsilon to a dimension. So now the pre-image of this. So these balls. So these are balls centered at some du xi. Okay. So then, so let this ball is bi. So union of d square u minus inverse of bi is measure of d1, right? And measure of d1 is like 1. So one of the balls, the pre-image has to have good measure. So there exists some bi such that measure of d square u bi is bigger than equal to epsilon to n square or n to the 4, right? So let me call it epsilon naught. Related that, clear? Why? Because if all these norms are small, then by the countable subadditivity of these inverse images, then I will have that the whole measure is less than 1, right? Because the number of balls is only epsilon to the n minus n to the 4, right? If all the measures are smaller than this, then I cannot sum up the measure of d1. So okay, so suppose the ball is here. Okay, suppose the ball is here. So then let's look at the pre-image point. Okay, so ball is here. So now this ball, now I take my epsilon to be very small. So therefore there exists some ball. So now I will do the argument that I will use the argument, even though I know that the diameter of d square u is 1, I will use the argument that as soon as I have diameter of d square u d1 is bigger than half, then I will use another covering. I can get rid of one ball. Okay, so I will do that covering later. But first, so what I want to first say is that because this bi is very small, at least there is some ball here or here such that the distance of this bi from some bj is bigger than 1 by 4, right? Because otherwise, if both the distances are less than 1 by 4, the diameter would be less than half, right? You can make 1 by 4, 1 by 16. I don't care. Okay. So now what do? I know that d square. So this d square inverse bi is bigger than this because this has to cover the measure of this, right? So therefore, so let this set be a, which is d square u inverse of di. So this is a set in B1. So let this be the set A. So that the measure of A is bigger than equal to some epsilon naught. Now, the one property that I use is that since Pj has a center, right? This Pj has a center. So Pj is like d square u of some y, right? And such that f of d square of u of y is equal to f of d square u of x equals to 0 for all x in A, right? And then if I use the ellipticity, what I get is that d square of u of y minus d square u of x plus has to be comparable to d square u of y minus d square u of x minus it is comparable to norm of d square u of y minus norm of d square u of x, which is bigger than equal to 1 by 4. Why? Because I can take the difference and write it in a differential way. So what I'm trying to use is that if f of m equals to f of n, then n minus n plus is comparable to m minus n minus, which is comparable to norm of m minus n. And why is that? Why? Because I take the difference, right? I write it as a differential sort of relation, which is I write it as f of tm plus 1 minus tn take by d by dt of this integrated from 0 to 1. Okay, and this will be equal to, by fundamental theorem of calculus, this will be equal to when t is 1 it is f of m, when t is 0 it is f of n, and this is equal to 0. Okay, So then what happens? If I sort of open up that, that differential, what I get is that 0 to 1 del f del ij, well, this is a bad notation, but let it be what it is. M minus n ij equals to 0. And this structure is uniformly elliptic, right? Aij. So therefore, this tells me that m minus n plus will be the same as m minus n, which is over there on the top. The top. This claim is true. Okay. So now, how do I apply the claim here? Both the centers of the ball. So where do I have the balls? So these are the balls, right? So ui. So this y is somewhere over here. This point is like d square of ui, and this is say the ball, which is d square u of a. So at each point, I know that at least there is a direction. There is a pure second derivative where it separates. Okay, because m minus n plus is comparable to n minus n. So there exists at least some direction where the positivity of d square u at this point wins over the positivity of d square u at this point, right? With regard to the difference. That is to say that there exists a direction E such that norm E equals to 1. What do I know? I know that this distance is like 1 by 4, right? So therefore this plus and this minus is also 1 by 4. So that means that there exists a pure second derivative where this thing is like 1 by 4. Not 1 by 4, it's up to an ellipticity constant but large, bigger than 0. So therefore there exists E. Because when I'm, what is this? This means that there is a pure second derivative where you capture a positive eigenvalue, right? So that means that there exists some E, norm E equals to 1, and that UEE of y is bigger than equal to UEE of x plus some, let me call it something, not 1 by 4. So let me call it some gamma, where gamma is universal bigger than 0 for all x in A. And what is A? Measure of A is bigger than equal to this epsilon naught. And now I use this lemma again. Remember what we had in the morning, the same thing survives for the non-divergent structures. That what is UEE? UEE is a subsolution to a non-divergent uniformly elliptic equation. That is, this is the max. So now this what I can do is that this I can majorize by supremum of UEE over B1. Right? This I can majorize by supremum of UE over B1. So what do I have? This distance is gamma. At least there is a set. So this distance is, this set is A. So a subsolution which is UEE is away from the maximum. So this is like gamma in a set of good measure. Why? Because the measure of A is bigger than equal to epsilon. Then it means that if I apply the Banerjee kind of lemma, that means that in a half the set, it is uniformly away. Anything that, so what does ellipticity do? Anything that it perceives in measure in the full set, it has the ability to reflect it uniformly in half the set. So therefore, if I apply this lemma, there exists a certain delta where it separates, which is to say that there exists delta bigger than 0 depending on this gamma and this epsilon naught such that UEE is less than equal to such that UEE plus delta is less than equal to supremum of UEE over B1 in B half. In half the set, it has to fall below by this. Okay, that means that if I now cover the same image which I earlier covered with epsilon balls, now if I cover it with delta kind of balls, ordered delta balls, okay, the image of d square u, then you take the ball delta by 2 ball, you take the ball where the supremum of UEE is attained. Suppose this is the ball where the supremum of UEE is realized, then this ball will not be present in half the coverage. Because in half the set, UEE has to separate by a distance which is at least delta. Right? Because if this cannot be in half the set. Because around UEE, there is a good separation. All distances on finite dimensional spaces are equivalent. Okay? So if it separates along an eigenvalue, in half the set, the separation also, you take the Hilbert norm square, okay? The Euclidean distance from there. So in half the set, so this is the point, suppose this is the ball, and this is the center, not the center, but suppose this is the ball where supremum of UEE is realized and this is of size delta, then in half the set, this ball is not present. So that means that in B half, I can get rid of one delta ball. Again, I repeat the argument. If diameter of B half is bigger than half, suppose it has not crossed one below, then again in the next step, I can get rid of another delta ball. In B1/4, I can get rid of, by the same argument, another delta ball. But what is the number of delta balls? Delta only depends on ellipticity over here, right? So the number of delta balls is finite. So at some point, if the diameter doesn't go below half, I will run out of my delta balls. Because the number of delta balls is like delta to the minus n4. And if at every level, so suppose I repeat, then I get that so if I repeat, then in B1/4, B1/2 square, B square U, I reduce another delta ball. But then, again, if I look at diameter of B square U, B1/2 square, if this is again bigger than half, again in 1/2 cube, I reduce another delta ball. So at some point, I will run out of my delta balls. So therefore, and the number of such delta balls, the delta is a kind of a universal constant bounded from below by a positive constant. So at some k naught, I have to stop this process. So that k naught is only detected by depends only on the delta naught, which depends on the ellipticity. So at some 1/2 to the k naught at one dyadic scale, the diameter has to fall below half. Because if it is as soon as the diameter is bigger than half, I can keep repeating all this argument. Okay. So this is the proof of the fact that d square u is in C alpha, and I have no time to do anything else. So that's all for today. Okay. Not for today. Jim has another.